Hi, and welcome to another video on fluid mechanics. Last time, we discussed new concepts of lift and drag, the global forces produced by the fluid mechanics we've been learning about throughout the course. These are concepts critical to fields of aerodynamics and hydrodynamics, where we're more focused on an object or vehicle moving through a fluid. Today, we'll extend this discussion to specifically discuss lifting surfaces that use special geometry to generate forces favorable to the designer. These surfaces induce pressure gradients, where the pressure varies in the streamwise direction and either helps or hurts the flow. And often, we see separation when the pressure gradient is strong enough, leading to a different and generally unfavorable flow state downstream. Our goal is to better understand the design of lifting surfaces and how pressure gradients can lead to separation. Let's jump in. We start by looking at a simple example of pressure gradients. Consider flow between two plates. One case has parallel walls, one has walls that converge from a large area to a small area, and one that expands from a small area to a large area. We're going to assume the flow is inviscid, so there are no boundary layers on the walls and the flow is uniform from top to bottom. We know something about the area relationship from beginning to end in all three cases, but what about the velocity and the pressure? To make conclusions about these, we need to consider our conservation equations. We start simple with the conservation of mass. If we consider the entire flow, we know that the flow rate in and out must be equal. The flow rate here is the product of density, velocity, and area. Let's assume the flow is incompressible, so the density is the same on both sides of the equation and can be canceled out. This means that the product of the velocity and the cross-sectional area must be equal at every point along the flow. If the area increases, the velocity decreases by the same relative amount, and vice versa. Thus, if the channel converges, fluid has to pass through more quickly to get to the same flow rate. Now that we understand the velocity behavior, what can we say about the pressure? Let's try the conservation of momentum equations, which have the pressure terms in them. Remember, conservation of momentum basically says the flow acceleration must be due to force, either through pressure, viscosity, or body forces. We have a relatively simple example, so we're going to simplify our Navier-Stokes equations. If you start with Navier-Stokes and you assume the flow is inviscid, meaning the viscosity terms go to zero, you get the Euler's equations. If you take the Euler's equations and you assume the flow is incompressible, steady, and you consider flow only along a streamline, you get the Bernoulli equation. The Bernoulli equation is everywhere in aerodynamics and hydrodynamics, and if you're interested, we dive a lot deeper into it in another video. Here, we loosely derive the Bernoulli equation, which states that the sum of the pressure and the dynamic pressure at a certain point on a streamline must be equal everywhere on that streamline. So, if the velocity goes down, the pressure must go up at the location to compensate. If we take this relationship and go back and consider our three-channel cases, we can now add in the pressure. For the parallel plate case, the pressure is equal at both ends because the velocities are equal. When the area increases, the velocity must go down, and as a result, the pressure goes up. Conversely, if the area goes down, the velocity goes up, and the pressure goes back down. When the flow slows and results in a higher pressure, this is called an adverse pressure gradient, because it is working to slow the flow down. This means that the flow pressure is increasing in the streamwise direction, so the pressure gradient is applying a force in the upstream direction. When the flow accelerates and the pressure decreases, this is called a favorable pressure gradient, because it is working to speed the flow up and is producing a force in the downstream direction. For an inviscid flow, the walls don't slow anything down, so the entire flow field accelerates and decelerates uniformly. However, what if we consider the viscosity? Here we're saying that the bulk of the fluid remains inviscid away from the wall, but let's allow viscosity to generate a boundary layer. That means viscosity is only important near the wall, which is generally an okay assumption in aerodynamics and hydrodynamics. Although these boundary layers are very small relative to the entire flow field, they're extremely important to the overall flow and forcing. Let's zoom in on our expanding flow where we consider a perfectly inviscid case and a case where we are allowing a viscous phenomena. For the inviscid case, the flow is uniform and slows down uniformly, nothing special. But let's consider a boundary layer. That means, in the region near the wall, the velocity is in a deficit, meaning it is lower than the free stream velocity. As the adverse pressure gradient pushes back on the entire velocity field, the region in this boundary layer can't fight back as much because the velocity is lower near the wall. At some point, the velocity just above the wall reaches zero, and can even reverse direction. The more the flow slows down, the more of the boundary layer reverses direction, meaning flow backwards. The point where flow stagnates and starts to reverse is called separation. Regions of separation have stagnated or reversed flow and can be very unsteady and generally wreak havoc on the local forces and pressure distribution on your vehicle. In this case, if this were an HVAC duct trying to efficiently move air from one place to another, this separation would lead to a pressure loss and it would take a lot more energy to move the same amount of fluid through. We also commonly see pressure gradients and separation in flows over curved surfaces. Consider flow over a cylinder or sphere. Generally, when the flow hits the front of the cylinder or sphere, it accelerates as it is forced to the top of the curve, or I like to think of it as going up the hill. Then, when it goes back down the hill, it slows down. This is because locally, in the front of the cylinder the flow is converging, and in the back it is expanding again. Zooming in, we see this. As the flow approaches the top of the hill, it continues to locally accelerate. This region has a decrease in pressure in the flow direction and is a favorable pressure gradient. At the top of the peak, the pressure gradient changes direction to being adverse because the flow must slow down as it traverses down the hill. At some point, the flow above the wall cannot resist the pressure force and reaches zero velocity somewhere above the wall, and eventually reverses direction. The first point at which you see zero velocity above the wall is called the separation point, and downstream of that you can consider a line where velocity is zero as the separation line. Below this line, the fluid is in the reverse direction, and above it the flow is in the typical streamwise direction. Now let's zoom out and consider what this means for the flow over the entire cylinder and the resulting pressure distribution. In the ideal case with no viscous forcing, flow bends around the cylinder and then flows downstream as if the cylinder was never there. We can overlay the pressure field to see that the leading edge and trailing edge points of the cylinder, there are high pressure regions. At the top and bottom of the cylinder, there are regions of low pressure as the flow bends around. In this case, there is technically no asymmetry in the pressure or viscosity, so the cylinder would not feel any mean force, no lift and no drag. However, if we considered a realistic flow with viscosity, the flow would be a bit different. The forward half of the cylinder would appear similar. We would have a high pressure region where the flow meets the cylinder, and then a gradual change to low pressure as it curves around the top. However, the flow hits the adverse pressure gradient on the top, and it does not take long for it to reach a point where the flow separates from the cylinder and moves into the free stream unguided. This leaves a large region of separation behind the cylinder where flow is low pressure, stagnated, and unsteady. As a result, there is a very large pressure difference between the front and the back, where there is a high pressure in the front and a low pressure in the back, which generates a considerable forcing in the streamwise direction on the cylinder. This is a drag force, and it's specifically called pressure drag or form drag. Let's consider another example to see how separation regions impact lift and drag. Consider a flat plate aligned with a flow. Here, there are viscous effects, and viscosity is the only source of drag on the plate. Once we start to angle the plate relative to the free stream, we start to see that the flow curves around the plate to the best of its ability. At some point, the flow separates near the back end. Here, there is both form and viscous drag, And now there's actually lift because the plate vectors flow downwards, which means there is a resulting upward force on the plate. We'll talk more about lift later in this video. As the plate increases angle, the separation region grows dramatically, and the flow spends less time attached to the plate. Finally, when the plate is perpendicular to the flow, the separation region makes up the entire back of the plate, and there is a significant pressure difference from the front to the back of the plate. As we learned in the last lecture, this means the flow form drag is high and there is almost no viscous drag. Let's take this behavior that we see and try to estimate a lift and drag curve of the plate as a function of the angle of attack, its angle relative to the flow. At first, the lift increases strongly, and the drag also increases, but a little bit less. At some point, the lift peaks near the point of flow separation on the plate, and the drag starts to increase a little bit more substantially. After separation, the lift plummets and the drag starts to dramatically increase. This is representative of separation characteristics generally in aerodynamics and hydrodynamics. Usually it penalizes lift and spikes the drag, and both of those things tend to be what the engineer does not want to happen. Regardless of whether the flow is laminar or turbulent, separation occurs. But the characteristics do change a bit if the flow is turbulent. Generally, turbulent flows are more energetic and have higher velocity near the wall, so they're much more resistant to adverse pressure gradients. To see this, let's compare a laminar and a turbulent boundary layer. The laminar boundary layer has much lower velocity in the region near the wall than the turbulent boundary layer. This means it's easier for the pressure gradient to stop the fluid in the laminar boundary layer than the turbulent boundary layer because it has much lower momentum near the wall. In other words, the turbulent boundary layer is more resilient against similar pressure gradients than a laminar boundary layer. Let's take this back and look at flow over our sphere again. First, we consider a smooth sphere with completely laminar flow. The flow hits the sphere, accelerates as it bends around the top in a favorable pressure gradient region, and then separates near the top when it hits the adverse pressure gradient. This results in a large separation region behind the sphere, and thus large form drag. However, if we made the sphere rough or dimpled like a golf ball, we promote the boundary layer's transition to turbulence. By the top of the sphere, the flow is turbulent and can make it much further down the back half of the sphere before it separates. This results in a smaller region of separation. We have essentially traded lower form drag due to the reduced separation for higher friction drag due to the attached boundary layer being turbulent instead of laminar. And the rough sphere can actually outperform the smooth sphere depending on the situation. Let's compare the drag coefficients of the two spheres as a function of Reynolds number. The smooth case has a drag coefficient that lowers with Reynolds number gradually until it reaches the point where the flow naturally transitions on a ball at roughly 10 to the 6, and then has a much lower drag because the flow stays attached much longer. Remember, turbulence reduces separation and leads to something called the drag crisis, where drag dramatically reduces when flow transitions to turbulence. If we plot the rough sphere on top, it has a slightly higher drag coefficient because it's rough that also gradually decreases with Reynolds number. However, because the sphere is rough, the flow transitions to turbulence at a much lower Reynolds number, nearly 10 times lower. This results in a small Reynolds number region where the rough sphere has a lower drag than a smooth sphere with the same diameter, which can be extremely counterintuitive. Coincidentally, this Reynolds number range corresponds directly to the typical Reynolds number of a golf ball in flight. This is why golf balls have dimples. Golf balls in flight happen to be at the perfect Reynolds number where the roughness reduces the drag and stabilizes the flight compared to a smooth golf ball. So, for the same impact from a golf club, the rough ball travels much further. These drag coefficient versus Reynolds number plots are common and are often also misunderstood because on the face it looks like the drag force goes down with flow speed or Reynolds number. And that's not true at all. The drag coefficient is going down, but the Reynolds number and the flow velocity are increasing. This means the flow drag force is actually increasing with Reynolds number. It is only that the non-dimensional drag coefficient is getting lower. So, generally speaking, turbulence helps you avoid separation because of this more energetic boundary layer. This is why you see little tabs on the leading edges of some aircraft wings or on the spoilers of custom street racing cars. These are called vortex generators, which induce turbulence and cause the flow to resist separation, thus reducing the drag and increasing the lift. Okay, now that we have a better handle on pressure gradients and separation, it's time to talk about airfoils. These are lifting surfaces specifically designed to promote pressure gradients to achieve lift while avoiding separation. Consider an airfoil, which can take many different shapes but is often portrayed almost like a sideways teardrop. When the foil has no angle of attack with respect to the flow, as long as it has no camber, it produces very low drag and generally little to no lift. As the foil gains an angle with respect to the flow, it starts to vector the flow over the top downwards, meaning the flow behind it is moving down when it came in coming straight. Through a mix of the Bernoulli effect and added circulation, this results in a net force upward on the foil, or the lift. Over the top of the foil, the flow is accelerating through a favorable pressure gradient and then slows down towards the back in an adverse pressure gradient region, kind of like we saw with the cylinder. If we overlay the pressure field, we see that underneath the foil we have relatively high pressure and we have relatively low pressure above the foil, concentrated near the leading edge. This pressure difference acts on the foil vertically and causes the lift force. Specifically, this foil would have high lift and relatively low drag, an ideal situation for aerodynamic flight. However, if we increase the angle of attack further, we reach the point where the flow can no longer handle the high pressure gradient as it comes down the foil and separates. This results in a much weaker suction region on the top of the foil, and as a result, the lift plummets and the drag increases. In most applications, angles of attack that result in separation are avoided because of this loss in performance. Regarding the airfoil characteristics, we won't go into too much detail because that's reserved for more aerodynamics-focused videos. However, we can cover the basics. A foil is generally streamlined in shape and it has an angle of attack relative to the flow when it is generating lift, and there is also always a drag component that comes with it. In aerodynamics, the lift-to-drag ratio is really important. The chord of the foil is the length from the leading edge to the trailing edge, a straight line. The curvature of the foil is defined by the camber line, which marks the midpoint of the foil along the chord. The distance from the top of the foil to the bottom at any point along the chord is called the local thickness. Airfoils come in all shapes and sizes, and often the design is based upon the needs of the designer. For low-speed flows, airfoils tend to be more blunt and thick. Commercial aircraft have more customized, complex, and thinner shapes. These shapes are tightly guarded secrets in industry and are heavily optimized. For supersonic foils, you'll see sharp leading edges and extremely thin foils to promote and control shockwave locations. The design really depends on what your condition and your needs are. What your flight speed is, your Reynolds number, your fluid type, whether it's water or air or something else, and what lift and drag you need. Now, let's say you've decided on a shape and you know your needs. How do you go about calculating the lift? If you have a very simple shape and a low angle of attack, meaning there's no separation, you can have some success analytically using the Kutta-Joukowski theorem. This relates the lift to the circulation that it produces by recognizing that the flow produced by an airfoil is the sum of a fictitious flow that does not vector the flow downwards and some circulation field around the foil. For more details, see the dedicated video on the Kutta-Joukowski theorem. However, for more realistic flows and foils, the lift needs to be obtained empirically. This means testing your foil in a scaled-down model experiment or doing a simulation on a computer and measuring the lift and drag. When doing these types of tests, using the drag coefficient to your benefit is really helpful. As we covered in the last video, the lift force can be defined by the lift equation, where the lift force is a function of the empirically determined lift coefficient, the planform area of the foil, and the dynamic pressure. This is just a rearranged form of the lift coefficient definition. This means we can measure the lift coefficient in a scaled-down experiment and then estimate the lift of a full-sized wing in realistic velocity. Commonly in aerodynamics, we consider an airfoil as two-dimensional and then multiply by some span to get an idealized three-dimensional case. However, most foils do have a finite span, and with that come end effects and losses. For example, consider a finite span foil extending from a fuselage. Here, the foil has some chord and span with the letters C and B respectively. The aspect ratio of the foil is how relatively long it is, which for a simple foil is the ratio of B and C. By design, the foil has high pressure underneath and low pressure on top, and this is what produces lift. What this does near the edge is creates vortex structures which induce their own drag on the foil that would not exist in a perfect flow. The most prominent is the tip vortex, which is the huge vortex that rolls up over the wingtip due to the pressure difference locally. These vortices take energy and thus produce an effective drag on the foil itself. So, we need to calculate and account for this induced drag if we want to have a realistic finite span foil calculation. Since the secondary vortex production is a result of the pressure difference between the top and bottom of the foil, it's fair to deduce that this must be a function of the actual lift. In other words, if we have a high lifting foil, we have a higher pressure difference, and thus we probably have stronger end effects. Prandtl developed an expression for an idealized elliptical shaped wing, which works okay for most applications. Here, the induced drag is the lift coefficient squared divided by a product of pi, span, and planform area. So, to get the real drag, you would need to take the idealized drag, which uses the ideal drag coefficient. This is the coefficient you look up in charts and empirical datasets. And then you include the induced drag, which is a function of this idealized lift coefficient. This approximation works pretty well, although getting something more accurate can get a lot more complicated. In practice, you'll need to calculate the lift needed for a certain aircraft such that it overcomes the aircraft weight. And the thrust is needed to overcome the drag, so that determines your engine power. Knowing how pressure gradients lead to lift and separation is a significant component of aerodynamics and hydrodynamics, and is widely used in these engineering disciplines. And that's it for lift and separation. Let's review. We started by using a simple channel flow with converging and diverging walls to introduce the concept of adverse and favorable pressure gradients through conservation of mass and momentum analysis. If you include the boundary layer due to viscosity, this adverse pressure gradient produces separation, a region where the flow is either stagnated or reversing in the flow direction. This separated flow is detrimental to the lift forces produced and enhances the form drag on surfaces, which is generally undesired in application. We learned that although both laminar and turbulent flows separate, turbulent flows are much less likely to separate due to the higher velocity near the wall. Airfoils are specifically designed to avoid this separation and utilizing the pressure gradient to their advantage in creating high lift and low drag. Lastly, we also covered how to account for the induced drag due to the flow structures that are a result of the finite span of a foil. Although we couldn't dive too deeply into aerodynamics and lifting surfaces and separation and all that, these past two videos introduce the basics you'll need in a bunch of different fluids applications in industry. And that's it. I hope you enjoyed the video, and thanks for watching.